So now we will discuss about transient stability. So what does transient stability deal with? It deals with the larger disturbances. Okay. Now let us say a fault has occurred. This will result in a large disturbance, right? So in that case, the auto reclose circuit breakers are going to start working. So what does an auto reclose circuit breaker do? It will trip immediately. That means it will break the circuit immediately. So the very first thing is trips immediately. So trips is nothing but it will break the circuit. Okay. Now after tripping, it will again reclose after a certain time. In that time, it will allow for the transient fault to recover on its own. Okay. Sometimes the transient fault, they will recover on its own. If they are not recovering, then they will require manual intervention. Okay. So it waits for a certain time before reclosing to allow for the transient fault to recover. After the certain time, it will reclose. Okay. Now this entire process, this is repeated 2 to 3 times, right? It will give 2 to 3 times chance for the fault to recover on its own. Okay. So but by that time, most of the faults they will recover. If not, manual intervention is required. Okay. Now what happens is, during the time that it breaks and again recloses, oscillations are going to occur in the machine. Okay. And during this oscillations, the system might fall out of synchronism. Okay. So that's why the clearing time of the breaker, it is of importance to us when we discuss the transient stability. So now we can move on to the discussion of equal area criterion. So the swing equation, as we know, it is a nonlinear equation, and for large disturbance it cannot be linearized. Okay. So some numerical methods are required to solve the swing equation. However, if you take a single machine, okay, a single generator which is connected to an infinite bus through some transmission network. Okay. So on the other end you have an infinite bus. In this case, we can make use of the equal area criterion to study the transient stability of the system. Okay. So single machine as well as coherent machines, right? In coherent machines, the machines will swing together. They will have the same swing curves. Okay. So the coherent machines can be lumped together to form a single machine. So in that case also we can use the equal area criterion. Now the very first thing that we are going to discuss here is the rotor dynamics during the fault. Okay. So once you understand this, it will be easier to solve problems as well as to understand the equal area criterion. First, if you consider the steady state, so we will now discuss actually what is happening in this steady state. Okay. At steady state, the machine is running at synchronous speed, omega s, right? So when it is running at synchronous speed, the displacement, the angular displacement of the rotor with respect to the synchronously rotating machine, it is going to be constant, and that angle we take as what? Delta, right? So if the initial angle, if you are taking as delta naught, okay, this is the steady state operating angle. Okay, the rotor is always maintaining a angular displacement of delta naught with respect to a synchronously rotating reference axis. And this is the rotor axis. Okay. So if you take the power curve, this is going to be, this will be delta and this will be the electromagnetic power. So this is going to be the sine wave. This is P max, right? Now if delta naught is somewhere here, then corresponding value will be the electromagnetic power, and also it will be equal to the mechanical input power, right? So we will take it as PE naught, the steady state electromagnetic power. Now let's say some fault has occurred so that the electromagnetic power is going to become 0. So that is causing the large disturbance. Okay. So if you take this power angle curve here, this is delta, this is PE. Now initially the operating point was here, let us say. This is delta naught and this was PE naught, which is also equal to mechanical input M. Now the electromagnetic power, this is electromagnetic power, it has become 0. That means it will fall to the x-axis, the delta axis. So now the mechanical input power, it is at this level only, but the electromagnetic power, it has come down to 0. Then what is going to happen? There will be some accelerating power. What is the accelerating power? PA, this is equal to PM minus PE, right? Now PM is greater than PE. So this is going to become greater than 0. That means there is some acceleration taking place, and when there is acceleration, what will happen? It will run at a speed, the rotor will run at a speed which is faster than the synchronous speed. Then what will happen to delta? Delta is going to increase, right? If this is the synchronously rotating reference axis and this is the rotor axis. Now this is moving at omega s. This was initially delta naught. When this was moving at omega s, this angle will be maintained because the relative velocity is 0. But now the velocity here, this is greater than the synchronous speed. Okay, omega is greater than synchronous speed. So there is a non-zero relative velocity between this and this axis. So this angle is going to increase. Okay, so that is why we have represented like this. It's going to increase. So now the circuit breaker, it will reclose after a time, right? So let us say after a time t1, the angle has reached some angle delta 1. Okay, and at that time the circuit breaker has closed. So now the new operating angle is delta 1. So PE will be this point here. If you can project onto the curve, this will be the new electromagnetic power. So the fault will be cleared at T is equal to T1, and by that time the torque angle has become delta 1. Okay. So now at this new point, the electromagnetic power is going to be higher than the mechanical power. Then what will happen to the accelerating power? It is equal to PM minus PE, right? So now that is going to be less than 0. That means the rotor will experience deceleration. Okay. So here rotor starts decelerating. Now one thing you have to note here is the velocity, it is still greater than the synchronous velocity, right? It has just started to decelerate. So after a time it will come back to the synchronous speed, but right now it is still greater than the synchronous speed, right at the point when fault is cleared. Okay. So this angle delta, it will go on increasing because there is a non-zero velocity here, relative velocity. So delta will keep on increasing, but omega is still greater than omega s. So delta will increase. Okay, so it keeps increasing even at this point. So we will use a different thing here. This will be how the delta is going to increase. Now at some point the speed is going to reach back to the synchronous speed, right? It is going to reduce back to the synchronous speed. So here omega is equal to omega s, but here the electromagnetic power is still greater than the mechanical input power, so it will further decelerate and the speed is going to be reduced. It is going to be decreasing below the synchronous speed. Now if this is a synchronously rotating axis and the rotor axis is now rotating at a speed less than synchronous speed, then what will happen to this angle? It will reduce. Okay, so from this point it will start reducing back, it will start falling back. Now during the time PE was 0, the rotor was under acceleration, right? So the area under this curve, this is the accelerating area. Okay, and after the fault has been cleared, when PE was moving along this curve, then the decelerating area is going to be this. Okay, so if this is A1 and this is A2, then A1 is the area under acceleration, Pm minus Pe, right, and A2 is the area under deceleration. Now according to the equal area criteria, these both should be equal. Okay, according to equal area criterion, A1 should be equal to A2. So basically the area under the accelerating power, PA d delta, this should be equal to 0. Okay, what is the limits here? Delta naught to, if this angle we are taking as delta 2, then delta naught to delta 2 should be equal to 0. That is the mathematical equation. So if you see in terms of the areas in the graph, then A1 should be equal to A2. Okay, now this is the first swing. Next, what is going to happen, like we discussed, once the speed reaches synchronous speed, deceleration will start, so it will start falling back. Now the rotor is going to oscillate about delta naught. Now what we are concerned about is the limit. What is the transient limit? Here the synchronous speed, it is achieved at this angle delta 2. Okay, now let us say this, what will be this angle? This is going to be pi minus delta naught, right, because at pi minus delta naught you will get the same value. So this is pi minus delta naught. Now let us say the synchronous speed is achieved at an angle which is greater than pi minus delta naught. Then what is going to happen? So we will draw this once again. Here we have the curve. Now initial operating angle was delta naught, and this is the mechanical input power, right. Now PE was 0 till an angle delta 1, and here it has cleared, the fault has been cleared, and if this is reaching till this point, let us say here omega is becoming omega s, then what is going to happen? You can see that this electromagnetic power, this is going to be less than the mechanical input, right. This is mechanical input, this is the level of the electromagnetic power. Then what is going to happen? The accelerating power PA, which is equal to PM minus PE, it is going to be greater than 0 at delta greater than pi minus delta naught. This is pi minus delta naught. Okay, so that means here it is, the rotor is undergoing acceleration, and once acceleration is happening, what will happen? Delta is going to increase, right. The rotor is going to have a non-zero relative velocity with respect to the synchronous axis, so delta will increase, and if delta is further increasing on this curve, what will happen? PE will further reduce, right. So here PE will further reduce, and as long as PE is reducing, PE will keep increasing. Okay, and once again when PE is increasing, once again this whole process starts. Okay, in this way the system will fall out of synchronism because the rotor angle will increase boundlessly. Okay, thus rotor angle will increase without bound, and rotor will fall out of synchronism. So this is when delta 2 exceeds pi minus delta naught. So what will be the limiting condition here? Transient stability limiting condition. This is going to be like this. This is the curve. Okay, so let us say this is the initial angle delta naught. This angle delta 2 should not exceed pi minus delta naught. So this will be the limiting condition for delta 2. Okay, so as it is, delta 1 should be such that this area should be equal, right? The area under acceleration and area under deceleration should be equal. So delta 1 should be such that A1 is equal to A2 and delta 2 is exactly equal to pi minus delta naught. Under this condition, we call this delta 1 as the critical clearing angle. Okay, delta CR is the critical clearing angle. That means at any cost, when delta reaches delta CR, the circuit breaker should close. Okay, and the time at which delta CR is reached, that is called as the critical clearing time. Critical clearing time. So this is basically how much time the circuit breaker has to wait before it closes, so that the system does not go beyond the stability condition, beyond the limiting condition. Okay, so that is the critical clearing time. This is the time for the circuit breaker. Okay, so that's why understanding that auto reclose circuit breaker, how it works, it is important. Now we will derive the expression for the critical clearing angle delta CR and the critical clearing time. Okay, so once again we will try to draw this curve, right? This is the electromagnetic power, this is delta, and the curve is going to be like this. Now say the initial operating angle was delta naught, this was the steady state, right? And this will be the mechanical power. So at this point the angle is going to be pi minus delta naught. Now when fault occurs, PE will fall to 0, and let us say the angle at which it is clearing, if it is delta 1, right? So this should be equal to delta CR. So when the clearing angle is at critical clearing angle, then this will extend, the decelerating area will extend till this angle, right? Delta 2 is equal to pi minus delta naught. Now this area is the area under acceleration, so we will take it as A1, and this area is the decelerating area, we will take it as A2. Okay, so according to equal area criteria, A1 is equal to A2. Okay, so from here we will find out the expressions for delta CR and TCR. Okay, so what is A1? A1 you can write as integral delta naught to delta CR, and this is the curve under which we want the area. So PM into d delta, that will be in the integral, right? So PM d delta, this is equal to, now here the area is in between this curve and this curve, right? So PE minus PM, and the limits will be from delta CR to pi minus delta naught. Okay, now what is PE? PE is nothing but P max sine delta, that is the expression for electromagnetic power, right? So minus PM d delta. So PM is anyways constant, so you can take this out. If you are integrating and substituting the limits, you will get delta CR minus delta naught, and similarly this will be equal to P max is constant, integral sine delta is going to be minus cos delta, right? So if you substitute the limits, cos delta CR minus cos pi minus delta naught minus PM pi minus delta naught minus delta CR. This expression, if you simplify, you are going to get cos delta CR is equal to pi minus 2 delta naught P max sine delta naught minus P max cos delta naught divided by P max. So here we have used the substitution, PM is equal to P max sine delta naught. So finally delta CR will be equal to cos inverse pi minus 2 delta naught into sine delta naught minus cos delta naught. This is the expression for critical clearing angle. Now we will find out the critical clearing time. TCR. So this you can find from the swing equation. What is the swing equation? md square delta by dt square is equal to Pm minus Pe, right? Now what happens at delta is equal to delta Cr, the critical clearing angle. Pe we can still take it as 0, okay, because just that point we are clearing, so we can take Pe as 0. So m d square delta by dt square will be equal to Pm. So if you integrate this one time, then you're going to get d delta by dt is equal to Pm by m into t plus some constant, right? And once again, if you integrate this, you're going to get delta is equal to Pm by m t square by 2 plus some other constant. So if you take as C1, C2. Now usually delta is equal to some value. So if t is equal to 0, then delta will be equal to C2. But at t is equal to 0, the initial angle was what? Delta naught, the steady state operating angle. So C2 will be equal to delta. At t is equal to 0, delta is equal to delta naught. This implies C2 is equal to delta naught. So you are going to get delta is equal to Pm by m t square by 2 plus delta naught, okay. Now at t is equal to critical clearing angle, delta is equal to critical clearing time, the angle will be critical clearing angle. So here you are going to get delta Cr is equal to Pm by 2m TCr square plus delta naught, right. So from here you can get the expression for critical clearing time. This will be equal to root over 2m by Pm delta Cr minus delta naught. So this is the final expression for critical clearing time.